Okay, I think we will wait a couple more minutes while people are still coming in. I think we can start the administrative part of the meeting. Welcome to the Thing Research Group interim meeting today. I'm Carsten Bormann, and Ari also should be here somewhere. Let's go through a few administrivia quickly. This is the chair's abridged version of the note well, which tells you that you may be recorded. Actually, you will be recorded when you say something in this meeting. We request everyone to be nice and professional, and remember, not everybody here is a native English speaker, so be patient with people who aren't. And also, we do use the IPR guidelines of the IETF, but they are written up on ietf.org/IPR for IETF purposes as well. Okay, so this was the short form. The long form is there's all kinds of problems with patent claims, submarine patents, and so on. And we have rules to work with these problems. I can't say work around, but at least somehow mitigate them. So please have a look at these IPR policies. Again, we are making recordings. The red "do not photograph" lanyard doesn't really apply to non-face-to-face meetings. So everybody who says something here is going to be recorded. And finally, we have a few rules, including a code of conduct, and if you experience something going on that shouldn't be going on, please talk to the chairs or talk to the ombuds team. The ombuds team is somewhat remote from any involvement that people in the research group could have. So that may be your best contact point if you are somehow not happy with what the chairs are doing, but there are RFCs you can read here as well. Okay, one important note-well slide is that this is the IETF, so we are focusing on longer-term research issues. We are not making standards. The IETF, our sister organization, is focused on shorter-term issues of engineering and standards making. So once we are reasonably satisfied with something we might be produced here, we may want to hand it off to an IETF working group to actually standardize this. And this, for instance, happened with one part of our data modeling work in the form of our contributions to the 1DM organization, which in turn provided their work as input to the IETF. So at least indirectly, we have one working group that was spawned from this research group. Okay, so I think that's the overall summary. Then there are a number of things that you need to know. Do we have note takers active at the moment?
Yes, I will be taking notes in the notes IETF.org, but anyone feel free to chime in.
Anybody else? Christian is a Zulip user today, and well, Marco is there. Hi, Marco. Marco will help out. Thank you. There is a chat which you can activate by using the two speaker bubbles on the leftmost bottom of the menu at the top of your screen. You can also start a separate Zulip application, but maybe you don't need that. We have a mailing list that you are welcome to subscribe to. It's not going to bury you in email, but it occasionally has some small bursts that should be quite manageable. And everything about this meeting is in the GitHub repository 02501 data models. Okay, so I think we can start with actually talking contents. This is a meeting that is focusing on data modeling, and we have been doing this for a while, just out of the observation that there are many types or classes of IoT devices out there. So getting some machine-readable information that can be used for talking to them will aid interoperability at the application layer. And doing this across ecosystems is really useful. So this work started in earnest in 2016 with the IAB's IoT workshop and was continued in the Wishy activity from 2017. So we are kind of child of Wishy here today. And I talked about SDF and how this became an subject for an IETF working group before. So right now, the questions that come from this side are of the form: how well does SDF stand up in applications? Does it work? Well, we don't know that it works, but how well does it work? What are the requirements that SDF does not cover yet? It used to be the simple definition format before we turned it into a semantic definition format, and it's still trying to be simple. So we're not trying to cover every last requirement, but we want to be really useful in this space. And what are the next steps we should go? So what kinds of experiments, specifications, and so on should we come up with or ask the IETF working group to come up with? So we have 3 talks on data modeling today. I will put in a few slides just giving an overview why these seemingly quite different talks actually fit very well together. And then I quickly introduce the 3 talks, and then we will go to the actual agenda of this meeting. So this is what we had in 2016. We found that we had various activities of different ecosystems. The horizontal lines are ecosystems here that described their devices in some form, from a PDF document to some XML, file, and we were more or less forced to write converters, tons of converters between all these different ecosystems and their data modeling techniques. And yeah, if it's a PDF document, that converter will probably include a human that actually reads the PDF document. And of course, we know that you solve problems like this by centralizing things, and the red star in the middle of this diagram became the objective of the wishy activities, and SDF essentially took the position of what we have now of the red star. We have to be aware that this is not a single piece of specification you can be doing. You can look at standardization in this space based on different levels or layers that you might have in your application. So you have an information model, which is about semantics, vocabulary, taxonomy, and so on. You probably have a data model into which this information model is mapped. And you, of course, need some form of serialization to actually send data around that matches this data model. So these three levels will come up again and again. And it's really important to remember all three of them must be under control for interoperability to actually happen. I talked about data in the previous slide. Actually, what we have here are interaction models. So you might try to do the same kind of layering at the interaction model level. It doesn't quite work out perfectly, but I think it's still a useful layering to have in mind. So there is just a difference between how do we actually send interactions over the wire, structural modeling, which is about how to construct interactions, and semantic modeling, which actually describes what the interactions mean. One other thing that we found was that while people initially were just thinking about translating data models, they are also thinking about translating data between data models. We were supposed to have a fourth talk today that was showing how to do this between Meta and lightweight M2M through converters with SDF in the middle. But unfortunately, the speaker became unavailable, so we will pick this up in another meeting soon. Yeah, so we will have three talks. One by Bart Brinkmann is about leveraging SDF models in NIPSI. NIPSI is non-IP control. So we provide IP access to non-IP IoT devices. And that, of course, means we have to support different ecosystems, such as Bluetooth, to actually make this happen. And when you do this translation, then the gateway can work better if it understands these devices to some extent. It doesn't have to have a perfect, deep understanding of how you measure turbidity in the water supply, but it probably should know that you have a sensor somewhere that can supply you with information about that. And it turns out SDF fits that bill quite well. And the one thing we need to understand is how to use the extension points we already provided in SDF to deal with ecosystem-related information, Bluetooth and so on. The second talk is actually not about SDF, but it's about Yang, which is another interaction modeling language that is almost but not entirely unlike SDF. Yang is interesting in the IoT context because we have an efficient message representation format for Yang now, Yang CBOR. And so it makes sense to look at Yang as just one of the ecosystems that we want to serve in this context. Now, the other thing that you should know is CNML, which is a generic data model for IoT message data, which we call CNML packs, because you have several records in a pack. And CNML also has an efficient CBOR representation format. But CNML is just a generic data model. It doesn't allow you to do application-specific modeling. So you are expected to understand all of CNML and to handle all of CNML when you're working with CNML packs. Now, the fun observation is that the representations we get out of Yang CBOR and CNML CBOR look very similar. So that's one thing that actually motivates looking closer. And the question, of course, is can we benefit beyond that interesting similarity? The third talk I will give about model evolution and dimensions of model evolution. So as a reminder, an SDF model describes interaction opportunities for a class of devices. So it's in a very specific place in the various diagrams and layers I had. And one observation is these are not fixed, but they evolve because of revisions, because of changing functionality. And also there's a need for variance of a device model for a number of reasons. Ecosystem-specific information may need to be added. And this gets interesting because the base models that describe what these variants have in common also evolve. So you have to have a somewhat orchestrated, synchronized move forward with the revisions of, with the evolution of the various models involved. And the keyword here is derivation. So we have some models that are not describing the entire world again, but are just saying how they are different from some base model. We also have the need to actually go from the class to the instance and describe instances of devices, or actually instances of the digital interface of a device. Again, there may be information that is ecosystem specific about that. And finally, the messages that we describe so nicely with an information model in SDF, those may need to be actually interchanged, and we need to describe how to actually get data models and serializations for messages. Okay, I think we have a quite interesting program for today. We have upcoming meetings. We will have a meeting that is security focused in about a month from now. We will have another data model meeting, but maybe not an interim in this format, but more hands-on meeting, maybe not recorded to YouTube like what we're doing right now. And we will take it from there. So this is not necessarily the last meeting this year, or most likely not the last meeting this year, but we will continue that, but we haven't started planning for the follow-on meetings to those. The next face-to-face meeting probably will be a summary meeting in Madrid. We found that very few of us actually go to Bangkok, so it doesn't make a lot of sense to have a summary meeting there. Okay, with that, 10 minutes late, but I will make up for that at the end. Bart.
Thank you very much, Karsten. Great, thank you. So, as Karsten pointed out, I'm going to be talking a little bit about kind of NIPSI and how we found our way to SDF and how SDF is being used in the NIPSI today. Next slide, please. Oh, I could do it myself, actually. Ta-da! All right, problem statement. This is actually a different or a slightly different representation of the multi-arrow slide that Karsten was showing us. So basically what we see in kind of enterprise deployments when you're looking at deployments of kind of wireless IoT solutions, and then we're talking mainly the non-IP protocols such as BLE and Zigbee, for example, right? We see proprietary stovepipes and vertically integrated solutions. So we actually took a bottom-up approach to the problem here and started with the idea of, okay, can we create like a gateway protocol, an API, right, that allows applications to basically communicate with these devices using a common API. And obviously, standardizing that API would make sense so that an application would know that when it goes into an environment that API would be available and could be used to communicate to these devices. Sorry. All right. So as I said, we kind of started bottom up, and we started with the API, and the idea was that the API needed to be able to do three things. First of all, provisioning. So we needed to be able to onboard a device into a network. We needed to be able to, especially from a non-IP perspective, we needed to have gateway APIs that allowed us to control or communicate with devices. And then we need an API that allows us to stream telemetry from those devices to applications. So from a provisioning perspective, we settled on SCIM, so System for Cross-Domain Identity Management. It's an IETF protocol as well from the SCIM working group, and SCIM has been heavily used, as you may know, to I would say transfer user and group information between systems. And what we did is we added a device schema so that we could basically onboard devices. The device schema has protocol extensions for specific protocols. So you could declare a BLE device, for example, and then the extension would determine what version of that BLE protocol is supported, how the device is onboarded, how do you connect to it, does it support BLE Secure, and so forth. But really focused on so SCIM's really focused on the instance of the device, and really doesn't describe the device more than what is required to onboard the device. Then NIPSI basically is a protocol that is being worked on in the ASDF group. And the goal of NIPSI is to be able to be a gateway API for multiple non-IP protocols. And here we support APIs that do operations on properties, for example, read or write a property, perform an action on a device, or configure an event for a device. Then finally, also part of NIPSI is a telemetry interface based on CBOR over MQTT or HTTP, and that allows us to streaming data from those devices, but also broadcasts and connection states, so that's devices coming and going. Now, when we started creating NIPSI, relatively early on, we started needing to, I would say, register things like properties, so that an application would, have a property and would be able to address a property. That property would be mapped to a protocol-specific property. So, for example, a property that is heart rate would be mapped to a BLE service and characteristic ID, for example, right? So we started by registering these properties individually to the gateway, but then very quickly we realized that there's actually data models such as SDF that actually can register a complete thing, including its properties, actions and events and so forth, in a model. So that's when we kind of realized that we could use SDF models to perform those registrations. So this is how NIPSI works today. So what you do is, if you want to do a NIPSI operation, is that obviously you have to declare the instance. We use Skim for that. And then all of the NIPSI operations would leverage Skim object IDs in the path. So so they're all against object IDs. And then also you have to declare the interaction model. So that's an SDF model. And that basically registers NIPSI properties, actions, and events with their protocol mapping. So what we have in the SDF model, or what you need to have in the SDF model to use NIPSI, is a protocol mapping to that SDF affordance. And those SDF models apply to either two IDs also, Skim objects, so either device or group IDs. So, 1 and 2, obviously you don't have to declare the instance first and then the model. You can do it the other way around as well. And once you've done those two things, then you can perform NIPSI operations against SDF affordances. So the protocol mapping is not required anymore because the gateway already has that protocol mapping registered from the SDF model, and then obviously publish those events as well. So there's a few deployment models that we see. So first of all, a simple model where a network gateway, which is both a Skim and a NIPSI server, talks directly to an application. So an application is talking directly to a NIPSI gateway. In this case, the application can import an SDF model of a thing, right? And then it can register that SDF model or part of that SDF model against the network gateway. An SDF model could be very expansive, and the network gateway may only need to understand certain properties and certain affordances. So either the complete SDF model is registered with the gateway or a subset of it. Now, we talked a little bit about those registration APIs. So that NIPSI does have a registration API to register an SDF model. However, you can also include the SDF model in a manifest, or it's basically an SDF a reference in the Skim object. So there's basically two ways to register the SDF model with the network gateway. So this is the simple kind of the simple use case. The other use case we see is that there's an application middleware. So this is typically a use case where you've got a network gateway that's sitting somewhere on premise, and that is speaking to middleware somewhere in the cloud, and then the application is speaking to the middleware. So here, the operations between the middleware and the network gateway are kind of pretty much the same, But what we see here now also, if an application leverages an SDF model, it will tell the middleware, hey, here's a SCIM object that I want to reference, and then specifically the embedded SDF model in SCIM will be used. So these are the two models that we've seen. So a little bit more about NIPSI registration. So this is basically how we tell the gateway what the interaction model for a device or a group of devices is. So to obviously, and it also tells the application, the gateway how to perform an action, an event, or how to do property operations on a specific device through protocol mapping. So there's so when you register a model, and we'll talk in a little bit about what a protocol mapping looks like. You'll register it for an ID, typically a group ID, right? Because a model will apply to a group of devices. And the top level could be an SDF thing or an SDF object, and then the gateway will basically leverage all the SDF affordances or make all the SDF affordances available for operations. And they create, so they contain protocol mapping. We have one other registration API, which is a data app registration. So this allows NIPS applications to register, targets for streaming events. So basically, it allows an application to register other applications to receive data for devices. So what does a protocol mapping look like? So a protocol mapping is basically tied to an SDF property, an SDF affordance, which can be an SDF property in this example. It uses a protocol map. In that protocol map, it has a reference to the protocol, and then the attribute that maps to the affordance. So in this case, we've got an SDF property of heart rate that kind of maps to a specific BLE service ID and characteristic ID. Protocol mapping, we want that to be extensible to new protocols. So you could register a protocol map for, we've got BLE and ZigBee defined now, and we could register other protocols, Ocean, Z-Wave, and so forth. Currently, we've defined a few protocol mappings that we use: properties, events, broadcast, connections, and all protocol-specific error codes. And a protocol mapping can be, obviously, is in an SDF model attached to an SDF affordance, but could also be used directly in a NIPSI API if an SDF affordance is not referenced. And then these are the NIPSI APIs. So basically, kind of three types of APIs. They map to the SDF affordances. So operations on properties. So these are puts and gets. So typically reads and writes of properties. Then events. These kind of stop and start events or get the status of a specific event on a device. And then there's one action ID. So that's a put that basically performs an action on a device. So these are all RESTful APIs with JSON schema. We have some, so NIPSI has seen some real-world deployments, although we're still working on it. So it's definitely not. We're still heavily working on it in the ASDF working group, but based on kind of draft specs. Some implementations are out there, both open source and vendors that are implementing it. And it's been deployed in use cases that do tracking of assets, for example, or tracking of people. It's been deployed in healthcare scenarios with patient vital sign monitoring, for example, in industrial settings and production process monitoring, door locks also, physical access control, and kind of connected or smart and connected building scenarios. NIPSI scales well. A gateway is typically deployed across multiple non-IP radios or access points. So obviously the goal here is to offer an application a single gateway function to leverage that entire footprint of access points. So it's been deployed across, we've seen deployments across tens, hundreds, and even thousands of nodes. And then we've seen also, deployments up to 100K plus devices supporting NIPSI operations and events. So it's a scalable. We find it to be a scalable approach. NIPSI and SDF, like what's our kind of real world in the field experience with that? So actually, a lot of the deployments that we talk about here are kind of the deployments based on kind of individual affordance registration. So remember when we talked through, okay, this is how we found our way to SDF, right? So we started with individual affordance registration. We don't have we don't have a lot of like in the field experience yet with SDF model-based registration with our partners, but we're quite bullish about that because it obviously really simplifies the approach and it makes it easier for application partners to integrate with NIPSI. So we really believe that SDF will make it much easier for applications to support NIPSI and to support a particular device. Okay, if you want to learn more about what we're doing, or even join in, if you're not already joined in, because many of you are. The IETF draft link is here, as well as the repo. There's very active work going on in the repo right now, and there's an open source project as well. So everything that we specify in the draft, we try out first in the open source project because we often find when we start the implementation, we often find things that are not quite how they should be. So the open source project is important for us as well because we want to make sure that everything we write up is actually tried and tested. And that's it. Any thoughts, questions, remarks?
Yeah, we have about 10 minutes for discussion. So if you have questions, please come forward with them now.
Thank you, Bart. I think this was very interesting. Maybe one small detail, if you go a couple of slides back, where you talk about the scale. So here you mentioned non-IoT devices. Wondering, was this non-IP devices or was this something else?
So where are we?
The scale, second bullet, 100K plus.
Non-IP. Non-IO. Oh, yeah, that's a typo. Sorry.
Okay,
You
that's
catch, you catch them all. I need to let you review everything I write.
okay. No, I was wondering if it's something specific,
Yeah.
but no, that makes sense. But then maybe a follow-up question. You mentioned that you're already getting a bit of experience, and there are some. You mentioned in the ASTF meeting that there's some models being built by partners. So when do you think we would maybe have some of those available? I hope they would be available publicly. We could also play around with them and see how people model things with STF.
During the course of the year, I'm sure. Yeah. So I think 2025, we should have some models available. We in the repo, we've added a few already for devices that we've tested with. But yeah, we'll definitely ask anybody implementing, if the models can be made available.
Excellent. Thanks.
So I have a question on slide 4, which doesn't have a slide number, but MeetEcho provides.
This one, right?
No. What was I looking at? Give me a second. Oh, it's 3. Sorry.
This one?
Yeah. This is intriguing because you are showing two ecosystems that are clearly non-IP, Bluetooth Low Energy, and Zigbee. And then you have Thread and Wi-Fi as ecosystems. Can you talk a little bit about the services the gateway provides for these?
Yeah, I do. Yeah, I thought you were going to ask this. So, if you look specifically, that's why we kind of like have these 3 different arrows here as well. Is that like the provisioning interface, right, is something that you could use for IP and non-IP devices, because you need to also, for IP devices, you need to declare an IP-based device when it joins the network. So that in that case, the gateway, if you kind of double click on this gateway, it's both a SCIM server and an IPSI server, right? So in this case, the gateway, we require the SCIM functionality of the gateway, but we may not require the IPSI functionality of the gateway.
Thank you.
Any other questions?
All right.
Since no one else in the queue, on the implementation side, how much of this is on the implementation, and where would you think like all the SDF things will be available for to experiment with?
In the open source, I think in the next month or so, I think probably by February, and then actually in the field, I think in the fall probably.
Great, thanks.
Lorenzo.
Thank you. Hi, Mark. Thanks for the great presentation. Can you actually go back on to slide 7? I have a question on the endpoint path, and I was wondering what's the rationale for having the parameter, the ID parameter, as a first element in the path.
Okay, so that's a very good question. So what we see, like when we talk scale, right? We end up we may end up in, or we're already seeing, we're ending up with situations where a single gateway is not able to serve like an entire network, right? So typically a network is built up of IoT radios, some centralized control elements, and then in this case a gateway function. So we already see scenarios where we may need multiple of these gateway functions, which means that if an application wants to talk to them, we'll have to have a proxy function in front of those, preferably an HTTP proxy. And then a specific ID will be attached, or a specific device will be attached to a specific radio somewhere served by one of the gateways. So from that perspective, what we think is that, if we have ID in the path, then we can basically, look up which gateway is serving in the proxy, look up which gateway is serving the ID, and then, basically with a simple lookup and an HTTP proxy find the right gateway.
Okay, thanks.
So I have one more question. Can you say something about broadcasts or multicasts? How do you handle a situation where you actually want to find a specific device that does something or get some information in a broadcast fashion?
Yeah, broadcasts and multicasts are very heavily used because it's fire and forget, so it doesn't take a lot of battery power, right? So we've modeled that as an event that an application can subscribe to. So because what we see with a lot of protocols, especially BLE, right? There's like most of the broadcasts are things that you're not interested in as an application, right? So what we do is we basically allow broadcasts are a NIPSI event type, and you can subscribe to a broadcast from a specific ID, so that you basically just receive the broadcasts that you want to receive and not have to listen to everything else.
Okay, so these are broadcasts from the devices to the infrastructure.
Correct.
Do you have the inverse direction?
Yes, there's a broadcast API as well, that which I didn't show here. So there's we discussed this in our last ASDF meeting, Karsten. There's a set of APIs that are like explicit connection management, and also like some explicit operations to devices, and broadcast is one of them. Yeah. So again, and here you can broadcast to a specific ID, right? But the thing is, obviously, other devices around that device would also hear that broadcast.
Okay. Thank you. Anybody else with questions, comments? In which case we finished 1 minute early. Thank you, Bart. That was very interesting. So we see it's actually being used with 100,000 devices. That's good. So the next speaker is Manoj about Cinema Yang. We already have talked about this previously, so this is mostly a follow-up. Please go ahead.
Thank you for that, Carsten. I'm not sure if I have the control to change the slides. Now I think I can. Okay. All right. Thank you everyone for joining. Thank you, Carsten Ari, for organizing this. As Carsten said, this is more of a follow-up. So the core ideas have been already presented in the earlier presentation by, I think it was IETF 121. But I'll give a quick context about what it is so that everyone's up to the speed. And then I'll also talk about some of the problems, some of the other things which have developed since. And hopefully, I'll try to wrap it up quickly because it's evening in most part of the world. Anyway, so why are we trying to do this? So Core-con CBOR encoding, what we found was very similar to Sentinel CBOR. And when we say Sentinel CBOR, that is, I think, commonly referred as compressed Sentinel. So sensor measurement list is a representation, and you can sort of encode it into CBOR, and then you can send it over the network. Core-con CBOR, although it was meant for a different application, if we can tweak certain things, we saw that, okay, the representation is almost the same, if not exactly the same. And why to do that is because if you see on the left, it's SNML represented as JSON. So it is about 134 bytes, more or less. In SNML CBOR, which is a sort of a serialized format, we see it's about 98 bytes. And then once we sort of move it to Core-con CBOR, it is about 89 bytes. However, we do have to add a module identifier. So 4 bytes extra for that. Yet it is still sort of more efficient for this example than the others. And this is not it, right? There are more optimizations to be found. And I have put like certain ideas out there, as in like certain literature, which actually try to attempt making it more efficient. So one is from Laurent, where he talks about if SNML is represented as time series data, how can we actually further compact it by introducing certain notations which are sort of found in CBOR template draft as well. And then there is an upcoming CBOR packed draft where they can further ensure that the data being sent is not redundant. So the gist of the idea, the gist of these drafts are like, assume your data modules are pretty much, or data structure is pretty much static, and the structure is static. So instead of sending the static structure all the time, all you have to send is just the variable parts or values, as they call it. So it becomes even more efficient instead of sending the whole tree every single time. But yeah, there has to be some context. There are some trade-offs, we can talk about it. But point of the matter, it can be even more efficient if SNML could be represented as Core-con CBOR. The other sort of why, which is if SNML had a Yang model, or once it has a proper Yang model, Yang actually allows you to add constraints, which is typically an implementation problem. So if somebody is using Python SNML, you have to depend on the library to check certain rules. With Yang, and because Yang has a much mature ecosystem, you have Lens, and then we have Pyang, etc. It can do it for you. You can add these constraints for SNML, and it can do it for you, and thus you can sort of be sure that if you just inherit or if you just use SNML Yang model, all these constraints, doesn't matter which library it is, you will probably be compatible. Your data will be probably compatible with SNML. Going forward, this is another sort of interesting point which sort of cropped up when we had a quick discussion with Carsten, Ari, and Laurent before, which is if SNML. Okay, so this is how I imagine it, and I'm nowhere an expert. I'm not an expert in SDF or Matter for that matter. But if SDF is at the center and there are other data models dancing around SDF, we need to sort of get into that ring and sort of get into the dancing ring. And for that, SNML has to, or the easiest way to get into that dancing ring is to be sort of converted to Yang. Once SNML has a Yang data model, then Yang can be converted into SDF. And from SDF, it can go and be part of every other data model, which we sort of say SDF is interoperable with. For example, Matter. So SDF, as we all know, that it can be thought about as a machine-readable ontological model, or in simple words, it's basically like how IoT devices interact and exchange data. One thing which SNML doesn't allow is to sort of have this rich modeling of, like, say, affordances, right? So you cannot have actions, you cannot have notifications. Yeah, you can't do that. But if you can sort of, if there's a Yang model for SNML representation of the data, you can add this information, and then there is a draft, or in fact, there is a tool already which converts Yang into SDF and SDF to Yang. some of the IoT devices use matter data models. So again, if even though the sensors are simple, your applications are no longer simple. So having that rich information being modeled into one of these Yang or other ones, which would actually allow you to build more interoperable and rich applications. So that's one of the sort of thought behind it, or motivation. Okay, so what are the issues plaguing? Again, I won't go into the detail too much, but more or less, what we see is that there are certain. So the spec was written in Senable without. Or let me put it this way: when we actually attempt modeling CoreConf into Senable representation, these are the issues which come up. For example, when you are when you are sort of assigning Yang identifiers with SIDs, you rely on a tool. But since SenML CBOR has a specific labels, you need to do that manually. Of course, it can be automated later, but you cannot rely on the tool directly if you are trying to represent SenML into CoreConf. So that is one. Second is CoreConf does not allow same SIDs for two different identifiers, and that means whenever you are representing data in CoreConf, you will never have a delta which is of the value 0. Now, for SenML, the label for n, the name, is 0. Now, this is a bit of a problem. We'll see in detail about this in further slides, but this is a sort of a deal breaker. So, of course, in the way we have done it is we have sort of hacked some things. We have sort of taken a creative license and sort of hacked our way into this. But again, this is a problem which either CoreConf has to fix or SenML has to fix. But in my opinion, I think the SenML specification can update itself so that there is a meaning behind the 0 and not an arbitrary label. Then again, the Yang model which we have prepared for SenML, it is in our draft, and yeah, it's not the best. So you can certainly add more constraints to it so that it can, you can model some of the units for your sensors. They can be identity refs so that, one, it will be replaced by SID identifier, assuming that you're converting it into CoreConf CBOR encoding, and then you can actually save some space there. You can also ensure that certain structures are for example, if S exists, S is a key, then V, VS, VB, VD are optional. So some sort of modeling guarantees can be provided in Yang, and this our model doesn't provide it yet, but if somebody can come up with this, it can sort of further enrich what we have. So again, I won't go too much in detail about this, but basically the workaround for n equals 0 issue. So in last presentation, there were some ideas, so I have sort of clubbed them and put some of them here. So this is the problem where, in fact, let me go to the slide number 2. Yeah. So if we look at the second one, you see 0. 0 is where step count is the value. So 0 is supposed to be the name, right? So if 0 is supposed to be the name, and 0 is obviously a CoreConf CBOR cannot have 0 as delta. How do we solve this? So one of the option is to actually say, what, let's just keep it as n. Okay. So this is sort of consistent with Yang SID specification. However, it sort of breaks SenML CBOR specification. So this is a bit of an issue. This is to say that basically n will never have a SID. So it will just be put as is, even in the CoreConf CBOR encoding. Yeah, so this is the label which we are talking about. Yeah, and then these suggestions are sort of clubbed together because they are sort of similar, which is why don't we have a different label which mean the same as name, or can we replace n with something else? Can we have a non-zero label or like a non-zero CBOR label for n? right? So which is something similar. This sort of allows you to be consistent with Yang seed specification and CNML CBOS specification, but it sort of breaks backward in compatibility. Now, this can be an issue if your applications heavily rely, or if you have a lot of historical data in CNML. So yeah, but yeah, this is one of the suggestions. Suggestion number 3 is can we have base name, which is so base name allows you to sort of remove the common parts of all your records, CNML records, and instead of sending it every time, you just send it once, and the data or the records after that will assume that this is the base name, and it will add it to your name. So it's sort of instead of sending it all the time, you just send it once. But to solve this issue, we just say that there is no name whatsoever, but you send base name every single time, so that you will never have to use the label equals 0, and it will be sort of consistent with Yang. It will be consistent with CNML CBOR labels, and it will be sort of backward compatible as well. But of course, it means it is less efficient, because there is a reason base name and name are different. And if you sort of do away with name, then you are losing something in the process. Okay, so what we sort of aim from the this interim, or the interims or generally from the community, is how big is the compatibility issue for CNML? That is what we wanted to sort of understand. And to understand that, we want to see how much or where CNML is used right now, right? So we see, and thanks to Ari, he has put a list of all the implementations in this link. And we see like the most common ones, especially for the Python, which is the easiest to start with. We see that, okay, it's not the Python ones is not very well maintained, but the C ones, which is used for embedded devices, was updated like 2 or 3 weeks ago. In academia, since 2021, we see about 214 research articles. About 17 of them are survey papers. So we see there is some sort of usage, but we would like to understand that, okay, is it easier to fix the original specification of CNML, or is it better to retain that backward compatibility? Then we would also like to understand or address some of the other issues we talked about before, and see if we are missing anything out. We would also like to figure out if there are better solutions for n equals 0, and sort of build consensus. And the larger story, which is what I was talking about in slide 4, which is can we actually head towards a more SDF centric model for representation of sensor data, so it becomes easier for everyone to play around, convert your data models from one to another. But I'm open to other ideas. Yeah, I guess that's about it. Thank you.
Okay, thank you for this overview. Do we have questions, Ari?
Yes, thank you, Manoj. This is interesting, and especially the bigger problem of like finding interval ways to also translate the data. And I think what you pointed here at, like, can we, for example, use the SDF affordance definition names as an easy way to go around here, and also apply compression, as you were suggesting here, we would have that common vocabulary. One thing I was wondering on the backward compatibility point. So, because what you are now proposing here, of course, is all new stuff. There's no implementations, maybe yours on this. So probably fixing the backward compatibility on that side is going to be much easier than trying to have those 10 plus CNML implementations updated. And I think that then it would have a lot of options to choose, how to deal with, for example, these Yang specific issues like the delta zero. So that at least to me seems like a reasonable way to go. But yeah, I think overall, what can we do to facilitate also translating data between ecosystems? I think it's very interesting. You have kind of interesting specific example here on the CNML and Yang, and can we like use either one of them or them together as the red stars, maybe picking up a few other ecosystems? I think that's kind of an interesting thing to take a look here, because of course both are rather generic Yang is perhaps better on the tooling side, where ZenML maybe has more on the I'd say IoT data and efficient ways to process it side, and see like what is the red star here that would be useful in general. I think that's a rather interesting question.
Yeah, as I said, right, like the SenML was meant for simple sensor measurements. However, the applications are no longer simple. And you don't. Yeah, if your sensors are like homogeneous, then it's fine. But if you have heterogeneous sensors, sensing one or more, and then it becomes really tricky, even if you want to use SenML. So.
Yeah, actually, if you have more thoughts on those points and like what are kind of tricky with ZenML, maybe that would be also interesting to discuss a bit later on, and kind of see like how could we do this cross ecosystem also on the data.
Okay.
So I think that's a kind of interesting point here. Thanks.
Okay. Thanks.
More questions? Okay, so thank you, Manav.
Thank you.
And hope we will have an interesting discussion on the mailing list on this. So we can go on to the final presentation. Which is about derivation and instantiation. Just to repeat from the intro slides, this looks so deceptively simple, but all these diagrams always look simple if you only have one of every kind. And much of the complexity, of course, comes from having more than one of any kind. We should look at how various models or instantiations actually relate to each other and how we can actually manage the process of evolving a data model. So I talked about this slide before. I have just included it here for people who just look at this slide set. So the real observation here is that we have class-based information in SDF, that we know that devices and their models evolve, that we need to support variance and ecosystem information. We have to talk about instantiation as something very explicit, and we have to talk about messages, in particular the data model and the serialization of messages. So just to take a step back and look at SDF again, SDF is about class-level information, about digital interaction opportunities. So it's not about the buttons that are on the device. It's about the virtual buttons that are provided by the network interface of the device. And we describe this using an interaction model, which has been said here already. And we call these individual interaction opportunities affordances. Was that a question? Or? We call these individual opportunities affordances. So that's maybe a weird word for people who are not into user experience, but that's a term we co-opted. So these are the main components of our models. And for these affordances, we actually provide information models for their input and output data. So we have some form, some level of description of the messages that actually go forward and backward when an affordance is exercised. And these information models have names in them, which are useful for humans who are reading these specifications, but need to be mapped to something by machines. And some of them actually also directly have some semantic information. For instance, the units is something in Celsius or Kelvin and so on. So that's what we have. And the question is, in which direction do we need to evolve this to have a better coverage of what we're trying to do? Now, one important observation is SDF models have no information about device instances. So obviously they describe an instance, but at the class level. They are not saying the temperature sensor that is in room 305 next to the door. That's not information that goes into a model, and that's maybe part of the discussion we are having in the ASDF working group about location information, which is information that applies to instances. Okay, so the main point I'm trying to make here is all these models evolve. And we have two components of the SDF base document that somehow deal with evolution. And one of those is versioning, where you can put a version into the info block of a model. The problem really is that these versions are just labels you can slap on the models, but there is no structure to them. So you don't know how versions of the same lineage are related. Well, you can do a lexicographic comparison of the labels, and maybe something that's greater than the other thing is newer or supersedes the previous one, and so on. But that's very weak. And for comparison, we can look at the really elaborate backwards compatible, non-backwards compatible rules that Yang has for its model evolution. By the way, that's an interesting observation, because these rules are probably too strict. I mean, they solve a specific problem, but they are probably a bit too strict. In the past, we have run into problems again and again where we couldn't make a change because it would have required a non-backwards compatible change of the model. And I think in the end, this needs to be possible if nodes that want to talk to a device actually know about the version that is actually deployed. So we also don't have a way to reference a version, or in particular to reference a sub-range. So this works with version 3.2 to 3.9 of the model, but don't use a newer model. That's something we just don't have a way to talk about. And also a related question is, who controls the lineage? So can I release that version 3.10? Or do I have to wait for someone else doing that? That's the processes for controlling this are not defined. So versioning is a way that, for instance, an ecosystem that closely manages their ecosystem-specific SDF models can use very well, but that's hard to use in a general context. The other component that SDF has for evolving models is derivation. So you can reference an existing model using SDF ref and then make changes to that. As we will see in a couple of slides, this is a structural mechanism, not a semantic mechanism, which has benefits and drawbacks. But an important question is, what is the relationship between a base model and a derived model? So we are not saying anything. It's a way to construct a model by referencing an existing one and importing stuff from there. But it's not clear why we are doing this and how the various interesting cases here need to be managed. But it's there, so it's a good thing that we have it. So just to remind people of how SDF ref works, essentially means we have a quality that you can essentially put everywhere that references using a query, which is a short form of writing URI, some part of an SDF model that is out there somewhere. So assuming that foo has been defined to point to my university repository or something, if I find an SDF data / temperature data in there, I could reference that in a specification. And we are seeing another example right out of the SDF-based document. This has a safety switch, which looks like another switch, but it makes two changes. It doesn't provide a toggle action because that can be really bad for a safety critical device because you don't know whether you're switching it on or switching it off. So you need reliable information on whether it has been on or off, and you can have race conditions and so on. So you probably don't want to do that. And our safety switch also has another affordance, which is an emergency stop button, and it's described in the parts I have left off here. So this is an example how to derive a model. So the safety switch is derived from the switch and has certain differences. Of course, if the base switch changes, then we might have a problem here. So yeah, the good thing about SDF-Ref is it's a very simple mechanism, so you don't need to say much. People can implement it in hours, and yeah, it probably can cover 80% of our objectives or even more. So it's really the answer to a large part of the things we're trying to do. But there are things that are suboptimal about it. And one is that the base model, the one that is being derived from, has no way to control or support that derivation. So the deriving model can just grab into the base model and do weird things with it, and the base model cannot really help it. And that may be good if the base model wasn't really designed with derivation in mind, but it's a lost opportunity for the base model to actually support the derivation. So to make sure that certain things come together when derivation is made, that there is some error detection there and so on. And that's also the second observation. If you do changes in your base model, since this is just structurally bound, the derived model is structurally bound, changes in the base model that have no semantic change suddenly can break derived models because they have a change in the structure of the interaction described. So that's a little bit dangerous. And yeah, generally these structural mechanisms are hard to process other than really literally. I mean, you have to have exactly the representation of an SDF model to do the SDF-Ref. You cannot do a model translation and then do a derivation because the model translation will mess up all your identifiers that point into the base model. Okay, one interesting question is, isn't this derivation mechanism a kind of subclassing? And the answer is, well, yes, you may use this in situations where subclassing would also be a solution. But no, subclasses in programming languages are a semantic derivation mechanism, and you might even have rules like the well-known Liskov substitution principle, the behavioral subtyping principle, where an object of a subclass can be substituted for an object of a base class. And that's actually pretty interesting because just because something follows the substitution principle at the digital side doesn't mean that it actually works on the physical side. So for instance, if you replace an on-off switch by a dimmer, that is, of course, fundamentally compatible. So all the places that are expecting only to do an on-off can use the dimmer as well, because you can, any reasonable dimmer you can turn off and turn on. But it's not guaranteed that the physical side will actually be compatible with that. So the physical side may have a wire going to a lamp which doesn't like dimmers, so it's starting to flicker and so on. So this is really an interesting question. What do we have principles like the Liskov substitution principle that we would really like to see maintained in such a derivation relationship? Okay, use cases. Where do we need derivation? In lots of places. You may want to make a variant of a device. So you have a device that works with 110 volts, and you want to make another device that works with 220 volts. And yeah, there may be a reason to do something to the interaction model to do that. Particularly if you have been short-sighted enough to make some interaction dependent on what the line voltage is. But you also want to be able to add features to a device. And that's maybe something where SDF-Ref pretty much shines. It does cover adding features quite well. The other use case is revisions. So why would you do revisions of a model? You might want to fix bugs. And that's one place where you really would be happy if the derived model, the updated model, would work in place. You might do revisions just to modernize an interface, make an interface easier to use, or to add features. So again, adding features is relatively nicely supported by SDF-Ref, but the other ones are more interesting. And then, of course, there are adaptations. So, for instance, adding a lightweight M2M object ID or a Bluetooth characteristic and so on to a base model should be a pretty easy thing to do. But again, you can do that. The SDF-Ref allows you to do that, but you cannot write your base model in a way that it is kind of prepared to do that, to have that done to it. So that's a limitation of SDF-Ref. So how do you actually pick up base model evolution? Right now, we only have a way to reference the base model by what is essentially a URI. That will usually be a specific revision of a base model, so you do not get automatic pickup of bug fixes. I mean, I'm talking about bugs in the model, not bugs in the implementation. But the advantage, of course, is that this can be fully controlled. So you can make sure that you don't get any surprises. An alternative would be to have the URI not point to a specific revision, but to point to the newest revision. And because we don't really have a newest relationship on revisions, this would essentially mean referencing any revision. So this can have a lot of automatic functionality, but it's dangerous because SDF-Ref doesn't have the semantic strength to detect when it's not yielding the result that you might want. Then, of course, there are sub-range references which usually come with something like semantic versioning. Yang people have been trying to get semantic versioning into Yang for like 5 years now and haven't quite succeeded, but that's maybe just an indication that some of the rules there are very, very strict. So we might want to make semantic versioning available as a useful concept in SDF-Ref. Yeah, so this is a choice that needs to be made. Then finally, let me quickly talk about instance information. Instance information might be information about the identity of a thing on the digital side, any supplementary identity information, which you might find in an asset management system or digital twin. Maybe its purpose in life or links that make it fulfill its purpose in life. And also maybe information about the physical aspects, like where is it? What are manual electrical settings? Is it actually getting 110 volt from the environment, or is it getting 230? And so on. So this is information that typically is not in the thing itself, because those pieces of information may be completely orthogonal to the operation of the device. This usually lives somewhere in a twin or an asset management. So this needs to be made available during instantiation. And I think the important observation here is that instantiation actually is an affordance. Well, maybe not is, but it has an affordance aspect to it. Of course, you cannot create a physical device out of thin air. So you cannot just take your model and say, make me a temperature sensor, and then you have one on your desk. But the interaction model may still want to describe the instantiation in some ways, what parameters are needed. So to start using a temperature sensor, you need to have its IP address or some other way to address it. You might have to do certain interactions during the instantiation process, including security interactions. You might have some information that is the outcome of this instantiation process. So for instance, there might be a number, a sequence number on a Modbus, or something might come out of the instantiation process. And as I said, the physical device probably needs to exist beforehand. So you have this interesting question, how do you refer to it before it has a digital identity? Okay, that's something that needs to be solved in one way or another. But right now, we cannot model this affordance very well. So of course, we can cheat and describe an instance using a derived model, making an instance by referencing a base model and then inserting instance information as constant properties into the derived model. Again, we have all the problems we have with SDF-Ref. We have no control. The instance information may not actually be constant, and not all instance information is actually meaningfully put into a property of the device. So that's not always the right thing to do. Okay, finally, I'm not going to go into details with this, but I just want to remind people that SDF provides an information model of the messages that go with interactions, but doesn't do the data model and or serialization level. So you can define your own standard for doing that, but that might not be interoperable with other environments. And you may want to add ecosystem-specific information there as well. Okay, I think we have 1 minute for questions. Sorry for running over. Manoj.
Thanks for the presentation, Carsten. One quick question about the versioning, right? So I didn't understand the part where, so basically is this, does the version flag offer any information about compatibility? For instance, if there is a major number, it means automatically that if the major number doesn't match, it means it must be backward incompatible somehow. If the minor number matches, then it's probably compatible. Is there any semantic notion to that? Or?
I only got half of the question. Can someone else answer that?
Yeah, I can answer that. So currently, I mean, we don't specify on that detail the use of versioning in the SDF models. We just say that they need to be comparable, but the semantic versioning, for example, is not enforced in a way that you could simply compare. An ecosystem may choose to use SDF that way, that they say, okay, it's always the same ver, and then you have, for example, the rules that you described, but it's not enforced by the SDF space specification at the moment.
Okay, understood. Thanks.
Thank you. Okay. I think we have reached the end of our allotted time. The meeting will not explode, so if you have additional questions, you can place them now. Milan, are you trying to put in a question?
Yeah, no, I'm trying to get in. I'm waiting for the permission.
Yes, please.
Anyway, so greetings from Sacramento Wine Festival. I wandered off into uses of IoT in viticulture. But so I have an off-topic question. As you know, I've been away for a while. Where does the Web of Things fit in this great scheme of things? Does it play in this space from your point of view? And basically, where does it fit?
Well, Web of Things was developed in a pretty close relationship with the work that we have been doing. So a lot of things are actually quite similar. Web of Things is not really designed to be the red star in the SDF way of doing that. So for our purposes, it's an ecosystem, but it's of course interesting ecosystem because it uses quite similar concepts. They even have an instantiation process. They have a thing description and a thing model, and the thing description can be derived from the thing model, but that process really is not the entire thing you probably need. But it's definitely an ecosystem that we have on our radar.
Okay, thank you.
Yes, great. Thank you, Karsten. And I think this presentation is a really good intro for our upcoming hands-on discussion, hacking all session around data models that we're planning to set up around the Bangkok IETF. So I guess there we can get into much more details also on the instantiation topic. Good, but I guess with that, we are running already over time, so I guess we have to close the meeting for today. But thank you also on my behalf, everyone joining and for the good discussions. And please, follow the mailing list for more announcements on the upcoming meetings. And talk to you soon again.
Thank you, everyone.